So hello everyone, welcome back to our radiation heat transfer learning journal. And in this video we want to start talking about our analytical solution. So what are we interested in finding? So what are we interested in finding? We are interested in finding usually two quantities, Q radiation, this is the heat flux scalar, and the divergence nabla bullet Q. Okay, and this is the vector, so I'm just going to put a vector sign there. It's a divergence of heat flux, where the QR there is the heat flux vector. So let's find the two relevant quantities. What were the expressions for them? So this is the heat flux vector. Okay, here's our heat flux vector. So our heat flux vector is basically, our heat flux scalar. First, we want to find our heat flux scalar. So the heat flux scalar, it's the scalar heat flux, right? Q double prime radiation. It is basically the solid angle integral of I cosine theta. So we've already gone through the derivations, not going to go through it again. Just going to leave the math as it is. And okay, so what is the expression for that? It is this. So we know that we want to find this expression. We first want to find I, expression of I, and we find that this is our expression for I. And of course, for 1D case azimuthal symmetry. Alright, so we take the dependence on phi out. Right, so we took the dependence on phi out, and yeah, we took the dependence on phi out. I think there should be a dependence on R as well, because the intensity is dependent not just on the the direction, but also this R. Okay, this R is the position vector. Depending on what the position is, it'll differ. So basically, we said the relevant quantity for R, the relevant quantity that we want to, the variable is tau, which is the optical distance from, the shortest optical distance from maybe the bottom plate. Remember, we're talking about this picture here. So yeah, we're talking about optical distance from, let's say, the bottom plate. And of course we have theta, which is the polar angle made from the normal to the bottom plate. So that's the polar angle. So no problem there. So so this is our expression when, yeah, so this is already in azimuthal symmetry form. Now we just want to include all the cosine thetas in there. We're talking about the cosine theta previously. I wonder where that is. Okay, hold on. Yes, we have this tau s equals to tau over cosine theta. So that's what we need to substitute in. So we need to substitute tau s equals to tau over cosine theta. So let's do that. Oopsie, let's do just that. Every time you see tau s, we will just put tau over cosine theta. Oops. Theta. And there we go. Okay, doesn't seem to be. You should. Theta. Okay. Yes, that's what I want. Okay, so every time we see a tau s, we just change to tau over cosine theta. And that will give us the radiation. So This one we kind of leave it alone, but we'll need to replace this tau s. Okay, becoming tau over cosine theta. Right. So what about this tau prime s? What about tau prime s? Okay, and d tau, right? D tau prime s. So again, it's not too difficult, right? Tau s prime. This is just not the full the length along. Yep, the length along here, right? Remember the projection of that in the vertical direction is just tau prime. So both of these are just again related by this right angle triangle here, and we have cosine theta here. So the relation is the same. It's just tau s equals to tau prime over cosine theta. And if we were to differentiate the tau s prime, okay, if we will differentiate this, cosine theta for a fixed theta is constant. Okay, 1 over cosine theta. Okay, so this is constant with respect to this anyway. All right, so yeah, why is it constant? Yeah, we for each tau prime s, theta is fixed, right? Yeah, for each tau prime s, the theta is fixed. Of course, if we vary theta, the tau prime s will vary accordingly. But yeah, in the case of this integration, theta only, I mean, the inside variable, theta doesn't change with tau prime s, right? So okay, what do I mean by this? As tau prime s changes, so this is tau prime s. Tau prime s can only change up and down this line. It can increase or decrease, but theta won't change. So theta is a constant. Okay, so that's why we kind of leave it as it is. Okay, but yeah. So as tau prime s changes, the tau prime will also change. So this is our relation for tau prime s over tau prime s and d tau prime s and d tau prime. So all you have to do is just substitute all the relations here. Okay, so yeah, we'll just substitute this here as we go, and we'll substitute this here. Okay, right, and then we see this quantity cosine theta actually pop up a lot, right? So cosine theta actually pops up many times. So very okay, so we see cosine theta pop up a lot for the 1D plane, parallel plane case. So normally the normal practice is to, since cosine theta pops up so much, we'll just use tau mu, not tau mu, mu, we'll just call use this variable mu to represent cosine theta, because we don't want to keep writing again and again. And basically the only way theta really matters is via cosine theta, right? Because we don't see the sign of theta coming anywhere else except in here, in the sine theta case. But you see, when we have sine theta there, it's just the derivative of cosine theta. So we can express that, or we can express that in derivatives of cosine theta, or d cosine theta. And what's the derivative of cosine theta? It is minus sine theta. Okay, so the only way theta matters is via these two. So usually we can just substitute all theta relations with mu. So we can just change variables here, very simple. So instead of theta, we can just put mu, because every time you see theta happening, is usually a sine or cosine of theta. So we can just talk about having that, leaving all these variables in terms of mu instead of cosine theta. It will make life a lot easier. Okay, so this should be tau s prime. It should just be depending on mu. Theta is a mu dependent. Okay, so this will be mu, tau over mu, tau prime over mu also. Okay, so d tau prime will be again divided by mu at the end of the day. So this you can kind of bring out because it's a constant. It's not going to change for fixing a mu. All right. So at a fixed mu, this mu here doesn't change. So you can kind of bring it out of the integral because it doesn't change with tau prime. Yeah. So having that all said and done, what do we do next? We still need to actually substitute it into our. We need to substitute into our q tau theta relation, right? Or rather, just the q, the scalar heat flux, right? So okay, first thing first, we can start by simplifying. Okay, you can start by simplifying. Use azimuthal symmetry assumption. Why am I doing that? I shall show you shortly. Okay, azimuthal symmetry assumption gets rid of the phi dependence on I. And basically, we'll change this to a tau, right? And 1D assumption, apply 1D case. So that means the only coordinate that matters is tau. Okay, so first we can integrate with respect to phi. So that's very simple. We just have a 2 pi in front, and we'll just get rid of the d phi. Okay. Next thing, we want to get things in terms of mu. So cosine theta, we'll just replace it with mu. Okay, and what is this? Okay, I forgot to write d theta. Yeah. So anyway, so what is sine theta d theta? Sine theta d theta. So if we were to again do a differentiation, d by d theta of cosine theta, that is just minus sine theta. So what is cosine theta? Cosine theta is actually just mu. It is the same thing. So we can just write d by d theta of mu, d mu. And what we can see is d mu equals to minus sine theta d theta. So sine theta d theta, it is actually just minus d mu. It's just a simple, replacement of variables. So that's the second thing we need to do. So all these are like intermediate steps. I'm like changing stuff here and there. Minus d mu, right? And then we need to change the limits of integration. So when cosine theta, what is cosine theta? What is mu? Or what is cosine theta? When theta equals 0. Okay, so I'm just gonna open a random Excel sheet. Okay. So okay, let me delete all of this. Okay, that was my old homework, but whatever. Okay, so first you want to have a cosine of 0, which is just 1. So cosine of 0 is 1. And what is cosine of pi? Okay, so cosine of pi, pi equals minus 1. Is minus 1. So let's say cosine 0 is 1. So we should have mu equals 1 to mu equals minus 1 here in the integral. Right. So if we were to incorporate the minus sign into the integral, we will have from minus 1 to 1, and we'll get rid of the minus sign. And this is basically what we are getting. So you have I tau theta. Okay, so in fact this one, as we saw before, the only thing that matters is really the cosine of theta. So we can just say I tau, the heat flux scalar is just I tau mu d mu. Integrate from mu equals minus 1 to mu equals to 1. Right, so let me just do that very clearly. Mu equals to 1, minus 1 to mu equals to 1. So that just makes it more clear. So what is our expression of I tau mu? It is this expression over here. So we can substitute I tau mu there, from mu equals to minus 1 to mu equals to 1. Right, so there we go. We can just substitute and copy and paste this whole thing here. Bam. Alright, so yeah, we just leave the source term as it is. It depends on the kind of scattering and emission you get, but the rest of the stuff we can actually start to integrate, because all of these actually have mu in there. So how do we do this? How do we do this mu integration? Next step, we do integration with mu. Yeah, so we have integration with mu. So how do we start doing this integration with mu? We need to start looking at the diagram again. Okay, so again, remember all of these, the physical meaning is still the same. So again, we have our two parallel plates, no problem. Let's zoom in a little bit. We'll have our two parallel plates, one at the top. Okay, I'll just do roughly parallel, right? Not exactly parallel. So we'll have this point here. We'll have an intensity, let's say here. And remember, we said it's very important to have our normal. Wait, I should use this. We'll have our normal there. This is the normal. It looks more like a H than N, sorry. Come on, you do a proper N. Okay, there you go. That looks better. Okay, the normal. And the polar angle here is theta. Right. So tau s will be here. Tau s prime will vary along tau s depending on how you vary it. So that's what you need to integrate. So what is important? This is, remember, the emission, the intensity coming from the bottom plate, the initial one, we call it I omega. As in this case, that's why it physically means I omega. And then it's going to attenuate according to exponential minus tau mu, minus tau over mu. So it's going to, okay, depend on this length, tau s, right? Because tau s, remember, tau s equals to tau over mu, where the mu is actually cosine theta. Right. Okay, so mu equals to cosine of theta. Pardon me, you're just using the mouse there to write. Hopefully it's legible. Okay. So, that's not a problem, right? Yeah, that's not a problem, right? So, yeah. The only thing that really kind of matters, right? Let's say we have mu theta going from 0 to 90. Okay, 0 to 90. All right. So theta going from 0 to 90, it will mean that, okay, let's say theta equals to 0. If theta equals to 0, then the start point of radiation will be from here, from this bottom plate. Right, from this bottom plate, going up, this is theta equals 0. So the I omega will be here. Right? That's not a problem. You increase theta, then maybe I omega will be here. You increase theta some more, I omega will be here, and you'll go all the way to the left, or depending on how if you have a radiation coming in this way and this is the theta, you'll go to the right. Doesn't really matter since it's azimuthal symmetry. The only thing is that when theta equals to 90 degrees, something interesting happens. It means that the radiation is coming from I don't know, infinity, right? It's going all the way to infinity. Okay, so that's a interesting point. At 90 degrees, this I omega will be from some point at infinity, right? So what happens if we have it past 90? Theta more than 90. Theta equals to 90 to 180 degrees. Or in terms of radians, pi by 2 to pi. Alright, so the picture is slightly different. Okay, picture is slightly different when theta is actually more than 90 degrees. So again, let's have our two plates here, and then our normal going from down to up. Right, so let's see. We have theta more than 90 degrees, theta more than 90 degrees. So what happens? We're going to draw that line up there. We'll notice that I omega actually starts from the top. Starts from the top. So I omega starts from the top. It will get attenuated by this length, and then I mean the rest is pretty much similar, right? But I omega starts from the top. So that's kind of a bit of a problem there. Why? Because I omega at the top will not be the same as I omega from the bottom. So this is I omega from the top plate, and this is I omega at the bottom plate. And yes, that will be kind of a problem. And this length, this is the tau s, right? Tau s, it is not this tau. Okay, it is not this tau over cosine theta anymore, right? Because then if cosine theta is more than 90, where theta is more than 90, right, so cosine theta less, for theta more than 90, or theta equals 90 to 180, right? 180. Okay, cosine theta becomes less than -1. I mean, oh, less than 0. Less than 0. So with these so-called geometrical problems, we will need to kind of separate two cases, right? Two cases. Case 1 is where theta is less than pi by 2 and more than 0. Case 2 is where theta is between pi by 2 to pi. So again, we have that problem, and we'll need to segregate these two cases out. So I'm going to copy the bottom, the top and the bottom picture. Okay, top and bottom picture. Okay, so we have two cases to consider. One is theta from 0 to pi by 2, and second is theta going from pi by 2 to 180 or pi. So how do we deal with these two cases? We'll talk more about it in the next video. Thanks for watching. I'll see you guys again.